Are you a student who has a strong passion for the aerospace industry as well as programming? If you answered yes, in this video I'll be showing you guys how you can simulate a rocket launch using MATLAB or any other programming language from start to finish without having much knowledge of rocket and orbital mechanics. We'll be doing a simulation of the NASA Space Shuttle launching from Cape Canaveral Air Force Station into orbit. Starting off with our fundamentals, we have a rocket flying in the atmosphere. We can draw a line for its axis. The Space Shuttle main engine generates a force pointing in the front. As the rocket flies, there will be a drag force which is opposing the motion. The rocket has its weight, which is mass times your gravitational force. And there's also a pitch angle, which tells its attitude and heading. Next, we have our equations of motion. We have velocity as a function of time. Our pitch angle also as a function of time. That's your gravity turn maneuver, which they call for orbital launches. Our downrange distance and our height also as functions of time. These are our ODEs. Our inputs will be your force, your mass, and your mass flow rate. They'll be discrete values, so we need to interpolate them to make them continuous. They'll be imported from Excel, from a spreadsheet. The atmospheric properties are important here. We have temperature, pressure, and density changing as a function of time, and it can be obtained from the NASA Glenn Research Center website, which is linked below. Our input values will be shown over there. Make sure you have it set to A1 as your first value, and that's our file name used. So now let's jump into our algorithm written in MATLAB. To start off, we have our XLS read function to import the values from your Excel sheet. I'll be calling my time array, my force array, mass array, and my mass flow rate array. They'll be used columns 1, 2, and so on, which is why I have a semicolon, comma, and my column number. I have a step size of 0.2 seconds, which is denoted by K. So now let's create our time vector from 0 to 590 seconds, which is about 10 minutes. Plotting the values, we can see that there's a jump in our force, which we need to make continuous and also fix. So let's interpolate our force by using spline, time, force, and your t. Do the same for your mass, so we can say time, mass, and t. Let's compare the length of our vectors, or arrays as you call it in programming languages. And when we plot our force and time, you can see a big jump at about 100 seconds, which we need to avoid because that's due to your interpolation inaccuracies. So to fix that, we should create a constant value. Same goes with the mass. We do have a jump there as well, as you can see here, between 120 seconds and about 150 seconds. So we need to fix that as well. We need to make it linear interpolated. So for your force, let's fix it between 60 and 120 seconds. Let's set that to a constant value. And we need to divide it by k so we can get the corresponding array element. And that number is from my Excel sheet, which can be seen over here. Also between 125 and 180 seconds, we need to fix the value as shown. So that's your force curve. Your mass curve, we need to use a while loop so we can create a linearly interpolated curve, which is very important because you want the mass to be changing gradually and not steep. So between 90 and 120 seconds, I have my interpolation over there. And first, let's set the variable names so we can track it. So let's update the mass linearly. So as you step forward in I intervals, and that's our formula for linear interpolation. And let's aggregate I by 1. End that. And let's again do the same thing between 120 seconds and 124 seconds. Let's keep that to a constant value. So between 125 seconds and 210 seconds, we can do the same thing here. Also use linear interpolation. We need to use absolute values, so make sure you have that down. So now let's set our final values. So after 510 seconds, the engine will generate no more force. And same goes for your mass. After 514 seconds, your mass will be your final mass of your empty vehicle at 74,000 kilograms. Now let's set the constant. So we have our Earth radius in there, in meters. Initial conditions, your gamma angle, which is just between 90 degrees and about 89 degrees. No drag, no force at the start because that's your starting points. Same goes with mass. We have our initial values in there, which you need to initialize our simulation. For the atmosphere, we have our density at sea level, temperature, pressure. At sea level, we're using STP conditions. And area, drag coefficient, and gravity will be constant for now, just to reduce the complexity of our simulation. Same goes with time. Velocity and impulse will be all zero at the start. Now let's solve our equations of motion. So let's make a for loop between that, and we will be using Euler's method for this. So let's set density. First, let's do the atmospheric properties. So we can set density, temperature, and pressure using that NASA formula which I showed you guys before. We are assuming that air is an ideal gas, which is why we can use P equals density times RT to set our density as well, which you can see me doing in just a minute. So the density changes with height, and we need to account for that in our simulation. And above a certain height, our temperature and density will vary linearly with altitude. So when we have temperature and pressure, we can set our density using the ideal gas law, which is pressure over RT. And we iterate the density to change with height. That's your RT formula over there. Temperature must be in Kelvin, so make sure you have that down. So drag forces, let's update that. The drag force formula is given by half density times velocity squared times your area times your drag coefficient. So now comes our first ODE, our speed magnitude, which we need to import over here. So VL plus 1 is equal to VL, and let's use Euler's method. So copy the formula into there and multiply it by your step size of h. You can see me typing the values in there. So force minus drag over m at a time interval minus your gravity times sine of your pitch angle, which is gamma. I'm calling it gam just for simplicity. Next, we have our gravity turn maneuver. Now keep in mind that we have to initialize our gravity turn, so we need to first pitch the rocket ever so slightly, and you can see me doing it over here. So between 15 seconds and 17 seconds I add a pitch. So this is done by our space shuttle main engines turning a little bit, and then we can implement our gravity turn maneuver, which is our gamma ODE, which you can see me doing over here. RE stands for the radius of the Earth in meters, and we're using trigonometry to figure out our pitch angle as a function of time as we loop for our simulation. Now let's come to our another ODE, which is my XODE. So the XODE can be done in the same way. Let's copy the formula from the equation into here, and we'll be using Euler's method, so make sure you multiply it by h again. So altitude, we have our last ODE in here, so dy over dt. So h means y in this case. So let's update that as we iterate from our simulation. So now we can just set a velocity component over there, and this stuff below here is optional. We can calculate our characteristic velocity from the rocket engine nozzle exit as we iterate, just for further knowledge and information, so we can track it as we fly our simulation. And specific impulse can be done the same way. The more impulse you have, the better it is. So that's simply velocity over gravitational force. And here I'm just setting constraints just to make sure that the simulation doesn't diverge. It stays defined at every time interval. So now we can plot time and our downrange distance. This can be seen over here. Same goes with our height. You can see it changing very quickly and then slowing down as most rockets launch. That's how it looks usually. We can also export our values into another spreadsheet called outputs.xlsx, and we can do this by using this syntax over here. So when we have our simulation done, we can actually view this into a simulator. So I use Flight Gear for this case, but you can use any other simulator you want. They have this Google Earth, X-Plane, and so on. I do have a video of linking MATLAB and Flight Gear for free, because Flight Gear is an open source software, so anyone can do this. I'll be linking that at the end of the video. So let's now look at how the rocket's flying in the atmosphere. So that brings us to the end of this video, guys. Thank you for watching. I hope you guys learned something new about aerospace simulations and how to actually program a rocket launch. I will upload this code onto a website in the coming days, and I do strongly encourage you guys to download this code and work on it for yourself, so you can actually get a better understanding of the simulation, and you can also test it with various cases to see how your flight performance is with different conditions of mass and force and so on. And that's it for this video. Thank you for watching. I'll see you guys next time. Take care. Have a nice day. Bye-bye.